Welcome to this Building Science speaker session hosted by Owens. My name is Dr. Hartwig Küenzel, and today I will be talking about European insulation materials and systems. Before we dive into the presentation, allow me to share a bit about my background. I'm department head of the Fraunhofer Institute of Building Physics, the largest research establishment in Germany for building science. Holding a PhD in civil engineering, I'm responsible for hygrothermal investigations sponsored by industry or public funding institutions. I have developed the hygrothermal model WUFI, which has become an internationally recognized and widely applied calculation tool for moisture control in buildings, and am active in many international projects, technical and standard committees within ASHRAE and CEN. And in fact, was the principal reviser of Chapter 25 of the internationally renowned ASHRAE Handbook of Fundamentals. From 1997 until 1999, and again since 2008, I've lectured to civil engineering students at Stuttgart University and have published more than 250 scientific articles in international trade journals, conference proceedings, and textbooks. In this session today, covering innovations in European building insulation systems, I will give an overview of new European insulation materials and systems, and will assess the suitability of several materials for different applications based on investigations carried out at the Fraunhofer Institute for Building Physics. Additionally, the performance of traditional insulation systems will be scrutinized, and potential problems and improvements will be discussed. Please note that we will now transition from this introduction to the presentation. And from this point on, you will simply see the presentation with my voice speaking to it. I hope you will find this presentation both informative and valuable. Achilles already talked about the topics I'm going to touch on today, so I will go into it and introduce first of all our institute and the Fraunhofer Society. Our institute is part of the Society for Applied Research in Germany, which is called Fraunhofer, and it comprises 59 institutes and has 18,000 employees and an annual budget of 1.7 billion euros. The institutes deal with a large diversity of research subjects, microelectronics, medicine, pharmaceuticals and things like that, and building science is only a small part of it. So there are only several institutes doing that, and one of them is our institute, and we have 3 locations in Stuttgart, Kassel, and in Holzkirchen. And this is our field test site in Holzkirchen, which was founded in the 1950s. And you see these different test huts here. They were built up out of different building materials, especially different masonry materials, because building materials were scarce after the World War, so we wanted to build thinner walls, and then we had more problems with dampness of the walls coming from rainwater penetration and also from condensation. And you see here the young fellow, this is by the way my father, who will become 85 this year. So he's measuring the surface temperature in order to find out whether we get condensation there or not. And here he's taking the climate data. So in the meantime, things have changed. There's still some of these original test huts, but we build many more. Some quite innovative things also. This is an inflated membrane structure, or this is here an office building where we test different facade systems and shading systems. And while we had problems with condensation in the 50s at the interior side, now, since we insulate much more, we have problems with condensation on the outside. Yeah? And when you get condensation on the outside, after a while, microbial growth is developing. You get algae and fungi that are growing, and therefore we are also interested on measuring the surface temperature here. And you see here the different approaches to solve the problem, and one approach is also to use low E paints on the outside, and you can see it here. They all have the same R value, but you see different colors because of that low E influence. We did a lot of tests on roofs, cathedral ceiling, adding insulation, so pitched roofs. You see here the wiring. And we also did investigations on flat roofs, especially inverted roofs and green roofs. There we were interested in how does penetrating rainwater affect the R value of the insulation, the effective R value, and how much water will, what you usually use is extruded polystyrene, how much water will that pick up over time? Because when you have rainwater penetration, you have water at the underside of the insulation slabs, and when you put vegetation, a green layer, so on top of it, then it's also very humid up there, and then they don't dry out anymore, and you get moisture accumulation. We have developed a test hall that is air conditioned, where we can compare the moisture behavior of different wall elements, as you can see here. And you see here we can take out the wall elements with a forklift, and then we weigh them, and that allows us to follow the moisture behavior, so to see whether there was water uptake or whether the elements could dry down. Just recently we have also done quite a few investigations on heritage constructions. So something like you see here, the half-timbered walls with different new infill materials and different interior insulation systems. And here we measure the air tightness of that system here. Yeah, let's now come to the major topics here. I wanted to talk a little bit about the German energy efficiency regulations. I think you have something similar here in the United States, but the most important thing to note here is that it's the end energy demand that counts. Yeah? So, and that end energy demand includes space heating, warm water supply, and the efficiency of heating and ventilation systems. And so you can trade off. You can either have a very good insulation or very good windows, or you could have, if your windows are not that good, a ventilation system with heat recovery or something like that. Just to give you an idea, if you have a reference building, here this square footage is less than 3,500, then the overall thermal transmittance of the building envelope would be around R14. That includes all envelope components. So this includes also the windows, doors, that includes all thermal bridges. All this is accounted for. Yeah? Because R14 doesn't seem to be that high, but since you include everything, it's far away from what the clear wall would have as an R value. When you have an existing building and you want to retrofit it, then the energy demand and energy demand may be 40% higher. But this is something you can only figure out when you remodel the whole building. If you just change certain components of the building envelope, let's say you do something with the walls, with the roof, or you change the windows, then this is what applies to you. Yeah? These are the U values that you have to comply with. So for pitched roof, 0.224, for flat roof, 0.2. This is for fenestration, 1.3. If you just change the glazing and if you leave the frames in place, it's 1.1. For walls in general, it's 0.24, so R24 would be that if you can only insulate on the inside, because either you have a facade that's protected or there's no possibility to insulate on the outside, there's no space or something like that, then it's 0.35, which would mean R16 that you have to comply with. And also the floors you have to do, if you can insulate the floors underneath, it's 0.3. If you can just put the insulation on top of the floor, you have to get to 0.5. So this is just to give you an overview of what the current regulations are. Of course, you can do much better, and there are incentives that are paid out if you do that better, if you undercut that energy demand. Okay. Well, since interior insulation is becoming more and more important, and also people are willing to spend more money on the insulation materials, because they're closer to where you live, and I just showed you how much or what the insulation thickness would be if you want to comply with the energy regulations. And I think this is the green part here where you should be in. So if you have a normal wall, masonry wall that's uninsulated, which has a U value of 1.8, so that would be a typical single wide wall or something like that. And you see here, if you have a standard insulation material with 40 milliwatts per meter in Kelvin, then you see you would need about 9 to 10 centimeters. If you have something that's very efficient, so goes down to 20 milliwatts, we'll see that there are materials around that have that, then it was much better. Then 5 centimeters of insulation would be good enough. So that's a great advantage. On the other hand, there are more and more people who prefer to have a kind of mineral foam insulation. We'll get back to that later. And we will also discuss why some people want this. And then you would have something like up to 60 milliwatts. And then you would need 14 centimeters, which is quite a bit. So you're losing a lot of space. Another problem is the moisture control, due to the high R values that you're getting when you apply such a thick insulation. Just to give you an overview of the insulation market in Germany, this shows you over the years what the percentage of the different insulation materials was sold in Germany. And you see that mineral fiber is with about 60%, by far the most common insulation material. Followed by expanded polystyrene with about 30%, and all the others are less important. They are down at about 5%. Also, polyurethane is around 5%. If you look to the renewables, which make up only 5% of the total market, you will see that cellulose fibers has the highest percentage of the renewables. So 30% there, followed by wood fiber insulation with 28%, and then wood wool cement board about 20%. All the others, flax, hemp, sheep's wool, and so on, are not that important. So now we get to the table. This is an overview of the standard insulation materials that we have and the typical thermal conductivity here. Please bear in mind that all these table values are design values of thermal conductivity, and they include a safety margin of 10 to 20%. So what you see here, if you measure the material, you would get a thermal conductivity that would be lower by 10 to 20%. I know it's different here, but in Europe we have this safety margin on it. So usually 35 to 40 milliwatts mineral fiber. The same would be for EPS. Polyurethane is can be a bit better. And here you see the vapor diffusion resistance factors. And they are quite important because they show you how breathable the insulation material is. That means how vapor can penetrate it. 1 means that it's the same as air. 30 means it's 30 times tighter to vapor diffusion than air, just to give you an idea about that. And here is another column that says, is it capillary active or not? So what that means? That means, does it wick condensate back to the other side if it happens? That means it's capillary active. So there will be liquid transport in it. So wood fiber board and insulated plasters could have a little bit, but we haven't measured that yet. We know that calcium silicate board is very capillary active, and that's one of the reasons why it's used a lot, or advertised at least a lot. And also mineral foam, and when we get to that, is capillary active. It's also interesting to note that our masonry materials that we are using, and mostly we use them without insulation, they are capillary active, of course. They are load-bearing, And also, their thermal conductivity is not that bad. And I will show you later how that is possible. Here you have a slide where you can see the different load-bearing masonry materials. I think here you mostly know CMUs or normal solid brick material. What you see here is all based on brick. So it's clay. It's extruded clay, porous extruded clay, and then the perforations are either filled with some insulation material like perlite, or here mineral wool insulation, or they're not filled at all, and then you have a lot of small air spaces in it. Yeah. And just to show you, if you have 36.5 centimeters, which is about 14-inch thick wall, that would be a standard wall that we are using in Germany now, you would get R28, which is not too bad. So you, in that case, you wouldn't need any additional insulation. You can put better windows in and a heat recovery system, then you would be okay with that without any additional insulation. And many people prefer it because it's easy to install. And also, I don't know whether it said it there, the last slide, yeah. About 40% of the walls here, so 45% of the walls in residential buildings are made out of that kind of brick. Also, when you look to insulation materials, what we usually do in Germany, we insulate our buildings at the exterior because you have almost no thermal bridges. It's easier to install, and you can install a higher thickness. But even though you sometimes have constraints with the space, because you're too close to a neighbor, or there might be other reasons. So we are getting better insulation materials, and one improvement that we've seen over the recent years is polystyrene insulation, which is the most common for exterior insulation of walls with radiation control. So you probably have seen that. That's that dark or gray stuff. This is what we usually did, and now we see more and more buildings that have that gray insulation on it. And you can see it here that you get an improvement of the thermal conductivity by about 14%, which is quite important. And you don't have to put up the density. So this is a very good thing, and therefore it's used more and more. There are some problems associated with it, and that is when the sun shines on them, they might expand, and it's more difficult to work with them. What you see here is a mixed board made out of the dark stuff and the white stuff. They call it Damascene. And here the improvement is only 11%, but you don't have that strong heat up when the sun shines on it. So this could be an alternative. Also, when we go to extruded polystyrene insulation, you will see also their radiation is partly responsible for the R value. You see that we get an improvement when we add graphite to the material, and the improvement is again 14%. Extruded polystyrene was much better in the past when we had the different blown agents, which are forbidden now, but now they are slowly getting back to where they've been. And the best material from the point of view of R value, with a thermal conductivity of 22 milliwatts, is a kind of very rigid board made out of phenolic foam. I don't know whether you've heard of that one. So you see that this is a very good thermal conductivity. On the other hand, because they're more rigid, they are more difficult to apply. And there might be other issues, corrosion and durability, where we don't know how good they will be in future. And of course the best, and I think Owens knows a lot about that, is the vacuum insulated panels. And they're also used now for exterior insulation systems, but they have to be protected. So usually what they do, they put another insulation material around it to protect it. And here It's even installed in a staggered overlapping way, so you also reduce the thermal bridges. And then you can really get down to 7 milliwatts per meter Kelvin. No. But since they're very expensive, they're only used if you really have to, because there is no space available. No? Otherwise, you probably wouldn't use them. Also with mineral fiber insulation, we have seen some progress. The fibers are thinner, I've been told. They are less itchy, better insulating. So we now get down to 32 milliwatts. And if you add aerogels to the fibers, like has been done here, you get down to 19, which is quite amazing. I've not seen the technical approval yet of that insulation board here, but I guess it will probably be around this 19 or 20 milliwatts. And this is a big advantage when you do interior insulation and you don't have a lot of space. And this is also what they market it for. And just wanted to show you another interior insulation material, mineral foam insulation. This is something close to autoclaved aerated concrete, but it's not structural. It's not load bearing. And this is the compressive strength that you get, 300 kilopascal. The boards are sold in thicknesses from 50 to 160 millimeters. And the lambda value is quite impressive if you think that this is just a mineral material. And it has become increasingly popular for interior insulation retrofits in Germany. So apparently more people are using that than any of the other materials. Other benefits are it's fire resistant, it's recyclable, vapor permeable, and capillary active. And we will get to that to see why that could be an advantage. And this brings me to the interior insulation challenges. And I think we've done exterior installations for many years. This is all well known, and there are usually not many problems associated with it. I know that you had some problems in this country with eave systems because you got rainwater penetration due to poor detailing and things like that. We always thought we don't have a problem because we have never seen problems, but we also get rainwater penetration, as we found out, only if you have a masonry structure beneath it that just accommodates that water and it can dry out during summertime. So it doesn't do any damage if it's not too much. Therefore, we never had any issues with exterior insulation systems. Well, now when you get to interior insulation, because you cannot insulate on the exterior side, and I've seen many buildings here in the United States where that's the same thing, all your brick buildings, you don't want to put anything on top of that, so you probably also have to insulate them on the inside. Then what are the consequences? First of all, you see that your temperatures are lower in the masonry in wintertime and higher in summertime due to the insulation. But this is not the main problem. The main problem is that behind that insulation layer, you may get condensation if you don't use a vapor retard or something like that. And when you get condensation, you will see problems like that, that behind that insulation layer, and here were polystyrene boards that were taken off, and you see this is all moldy. Only where the glue had been, there's no mold. But the small airspace between the old masonry and the insulation, mold had grown. So that is a problem that we have to avoid. Another problem may be that if you apply the interior insulation, then you can get frost damage. And we will see in the next slides why that is. And here you see tests that we've done at that air-conditioned test hole that I've shown you before. You see here, these are masonry, solid masonry wall elements, and they were exposed to wind-driven rain and to normal interior climate. And you see some of these masonry wall elements were insulated on the inside with, I think, 50 millimeter of polystyrene insulation. And in the beginning, they had exactly the same water content, and then those with the insulation became wetter over time. And you see that the main reason is that they don't dry as fast as the others. And why is that? That is because when you put insulation on it, interior insulation, it doesn't change the wetting. The wall wets the same during winter rain events as before, but it's changing the drying conditions. While before you had dry out of the moisture to the outside and the inside, now there won't be any drying anymore to the inside because you have your insulation with a vapor retarder. And also the drying to the outside is reduced because your temperature is usually lower there. And that affects it, as you can see here. So what are the different moisture control strategies that we've used in the past and what might be new now? So if you have interior insulation, either you don't put any vapor retarder, then if this is a masonry material, you would get condensation there, but the moisture will be redistributed. And whether it's a problem or not depends on that water absorption capacity of the material below it. In summertime, however, when the wall heats up, maybe because the sun shines on it, then you get good dry out also to the interior side. If your material here is sensitive to moisture, you have to avoid to get condensation. So what you do, you put there a vapor retarder or vapor barrier. That reduces your diffusion so you can avoid condensation. On the other hand, in summertime, when the wall heats up from the outside, you might have the problem that sorption moisture contained at that wall will go by vapor diffusion to the inside. Then you have here that vapor retarder that prevents it to dry out to the interior, and you can get condensation here, which is not a very good thing. And therefore, more and more people believe in, I say believe in because we're not sure whether it's really the best solution, in having a capillary active insulation material that's at the same time vapor absorbing and also liquid water redistributing. How does that work? Well, you get here your diffusion and you get liquid flow that wicks water back to the inside. And if you have a system like that, also in summertime, you don't have a problem with any drying towards the inside. And what's the basis behind it? The basis is if you look to a small pore in your mineral building material, as you can see over here, most common gradients you get in wintertime is vapor pressure gradient from the inside to the outside because it's warmer inside than it is outside. But your gradient in relative humidity is higher at the outside than it is at the inside. So when the material is dry, you get just vapor diffusion going in that direction. If you have more and more of that vapor absorbed to the wall of the pores, then you get a surface diffusion. And surface diffusion is governed by relative humidity. Because when you have a thicker film, the molecules move more easily. So, and this is opposed to vapor diffusion. And this means it's capillary active. And then if the whole pore, because it's small enough, is filled with water, then of course you get flow also towards the inside. So that's the idea behind it. The question is now, when does this process start to work? How much relative humidity do you need to get that surface diffusion going? And is there a critical limit? If it's getting too wet here, is that a problem? And what we discussed in the moment in Germany is that you should limit your humidity here to 95%. We don't want to have real water there because that would be too much for most of the wall materials and the interior plasters there on that. So how can we find out what the relative humidity, the maximum relative humidity would be there? Well, you do a test. And the best test you can do is a test that's similar to the situation that you will find in the wall, in the insulation material. And this is what we've done here. So we have such a test set up where we have here our insulation material that's capillary active or not. Yeah. And we cool it down at that surface, the same way as it would cool down in a wall assembly. And then we have here interior conditions, and you get vapor flux inside. Yeah? And then you will see either you get here condensation, or part of that moisture, it's transported back. Yeah? And once we've done measurements like that, what we do, we compare that to simulations. We try to simulate it in order to find out what the right liquid properties are. And you see here, you can do a sample weight change. We have here these weight changes. They take up some water, but if it were only condensation, it would go continuously up. But here you see it levels off. It levels off because you get this capillary wicking back of the water. And you can also see that when you do NMR tests. So you put your samples in the NMR where you can measure, without destroying them, the moisture distribution. So you see that here, moisture distribution. This is the sorption moisture distribution after 12 hours, 24 hours, 48 hours, and so on. And this is the dynamic equilibrium. So you can keep on doing the test, but your moisture distribution won't change anymore because all of the water that's going in, or the vapor that's going in, is transported back outside. Yeah? So that would be the equilibrium curve here. And if you put these results into your simulation, this is something we see here, and I show you 3 different cases, you can figure out what the humidity conditions will be behind the insulation layer. And I've chosen 3 examples. A standard case where we have masonry and just put polystyrene EPS insulation on the inside and then gypsum board. Then we have a capillary active case where we replace the EPS insulation by calcium silicate, which is known to be a very capillary active insulation material. And an alternative was that you have something what we call smart vapor control. So you have a very vapor permeable insulation material, in this case here a mineral fiber insulation, and you use a vapor retarder that is controlling the vapor flow. It controls the vapor flow in such an extent that you get less vapor flow in wintertime and more in summertime because it adapts to the humidity it sees. Yeah. So these are the 3 different cases that we've calculated. And what you see here, if your wall is not exposed to wind-driven rain, or when you have a very effective wind-driven rain protection, let's say a cladding or something like that, then this is when you do the simulation over several years, exactly with the material data that we have determined by our capillary test here. You see here the relative humidity. Here over time, this is winter, this is summer. And you see if you have EPS, well, you stay well below the 95%. Yeah, there's no problem. It's even better when you have mineral wool and that vapor retarder, humidity controlled vapor retarder. When you have that capillary active insulation system, then you get a higher relative humidity because it only starts to work at higher relative humidities. Yeah. So that doesn't look that good. It's still okay because it's below the 95%, but it's getting close to it. Yeah. Now, the situation changes if you have a wall that's exposed to wind-driven rain. So there's some moisture from the outside that's added to the wall, the moisture in the wall. And then you see, well, with the EPS, it's going to fail. It's going to be very wet, yeah, because there's not enough dry out towards the interior. And here you see, well, it's a bit better when you have the capillary active insulation materials, and it's also quite good if you have that special vapor control. Yeah. So yes, the capillary active insulation materials work. We're not sure whether they work that much better than what we usually know, and apparently having humidity controlled vapor retarder together with mineral fiber insulation does a little bit better than the capillary active. You know? But this is a discussion which is still going on in Germany because many people, as I said, are believers in these capillary active insulation materials because they think they're breathable. They don't want to have a vapor retarder. But I think we also have to teach them that vapor retarder is not equal to vapor retarder. It depends on the perm rating of the vapor retarder, how it actually performs in practice. So there was a question whether capillary activity can change over time. We have not seen that yet. No? So the materials that we have tested have not changed, but they were not applied for a very long time. Yeah? But in principle, it's possible that it could change, yeah? Especially if you get some pollutants into the system. Yeah.
Give you a false sense of security.
That could give you a false sense of security. That's right. Another problem with interior insulation is that you get thermal bridges at the details. Yeah? You see that here. And if you take just the clear wall insulation, then this is the U value you would get versus the interior insulation thickness. On the other hand, since we have so many thermal bridges, they become more and more important when you increase the insulation thickness. Therefore, it doesn't make that much sense to have a very thick insulation layer, as you can see it here. And you have to take care of your thermal bridges. Yeah? Here you can see them in a thermograph. You see the partition walls. So what could you do? Either you put insulation wedges on partition walls, or balcony slabs or whatever you have, floor slabs, which is quite important. And another possibility is, and that's also quite important, when you have windows, that you insulate the window opening. Yeah? But most of the time, there's very little space available. Therefore, it would be very beneficial if you had an insulation material with a low thermal conductivity, even if that material is much more costly or much more expensive than a normal insulation material. It might be worthwhile to have it there, because you don't have a choice. And there's another European standard requirement that applies, of course, to the whole surface, but especially to the thermal bridges, which is quite important. And this is the temperature factor. Yeah? Temperature factor has to be above 0.7. That means if you have 20 degrees on the inside and 0 degrees Celsius on the outside, then your surface temperature has to be above 40 degrees C in order to avoid mold growth. Okay, so this is the last item I wanted to talk about today, and that's the importance of air-tightness. And this is quite an extensive field study, or field test that we've done at the test site of our institute, and I'm going to talk a little bit about it in the last 10 to 15 minutes. I call this a French export hit. They call it isolation mince réfléchissante. So this is reflective film insulation, and that's something that's widely used in France now. And it's coming more and more to other European countries. And the reason why is it's very easy to install. You can do it yourself. And it's not complicated, and then you tape it, and it's quite straightforward. The problem is it as good as it claims to be? And this is a photograph I took myself at the trade fair, this international trade fair in Munich. You might have heard of that. It's every 2 years. And that was in 2009. And there they claimed, and you see that material here, that you get more energy savings with 1 inch of reflective film insulation than you get with 20 centimeters or 8 inches of glass fiber insulation. So this is amazing. Yeah? And must be misleading, but how can you prove that? And this picture was taken 2 years later. The same claims, there's one difference. Now, instead of saying glass fiber insulation, they say convective insulation. What does that mean? It includes, as you see, mineral wool, polystyrene, polyurethane. Yeah? So what's the background to these misleading claims? And the background is that they have done quite a few field tests comparing twin houses, so 2 identical test huts in France, in Britain, also in Germany, where in one test hut they applied mineral fiber insulation or polystyrene insulation, and in the other one they reflective film insulation. And then they measured the energy consumption. It turned out to be pretty much the same in many cases. So we also did a test for them because then they were quite bold and they thought, well, now we need a real institute to prove that this is right. And the first test where they installed the glass fiber insulation and everything also showed something like that. I can't show you the results because we had some legal problems with them. But I just tell you, it's possible if you have a mild winter day with a lot of wind, you get the same heat energy consumption, even a higher heat energy consumption when you look to the mineral fiber insulation. Yeah. And that was a big problem and was a real wake-up call for manufacturers of mineral fiber insulation in Germany. And therefore, we did another test. And that test we published, the other one we didn't. But before I go to that, we wanted to know what could be the reasons for that. What could be the reasons for these test results? Yeah? And I think it's quite evident. First of all, you can get wind washing. That's reducing your insulation capacity. You can get airflow through the insulation layer caused by pressure differences if the structure is not airtight enough. Yeah? And you could also get maybe latent heat effects. Yeah? So we know that this part was probably the most important thing that in most of the other tests we know of. Yeah? That the whole structures were just not airtight enough and they might have had wind washing. So therefore, I show you what kind of investigation we did. And you might not know, but in Germany, only about 10 to 13% of all structures are wooden structures if you look to wall structures. It's different when you have roofs. Yeah? The pitched roofs, and quite often we have these habitable attics. Yeah? They are insulated and they are wooden structures. It's the other way around, I think, here in the United States. And that's the reason why we took a habitable attic space in order to do that investigation. And you see here the two twin houses, and you see here these are all the data, the area. This is the total volume of both. This is the way they look. And this is what we investigated. Yeah? So one attic space or one attic cathedral insulation was equipped, as you can see it here, had an R value of 35. This is the metric R. This is IPR. And here we had, between the rafters, we had mineral fiber insulation, two types of mineral fiber insulation. We'll see afterwards why. This was high density, this was a lower density, and there we had the vapor retarder. And this is just what we have on the outside, the cladding of the roof. And the same thing with the other insulation, the refractive film insulation, where we put all the insulation beneath the rafter. This is the way they usually do it. They just staple it to the rafters, and then they put gypsum board on top of that. You know? And here now the question is, what are the R values? And this is red. This is what the manufacturer claims. R32, which is very close to what we have here. And this is what we've measured in a hot box test. R12, not more. And that includes the air spaces on both sides. So we installed it, we taped it. This is the reflective film insulation. Here we have the glass fiber insulation. And as I said, a higher density board at the exterior to avoid wind washing. And then lower density board at the interior here, you can see here. And of course, we looked at all the details. It was very well taped here everywhere. We wanted to get that structure really airtight. And then we took thermographs from the outside, also from the inside, in order to detect where there might be still some leakages, and then we sealed them. But we did this with both houses, not only with the one of mineral fiber. And in the end, it turned out these are the blowout tests that we've done. This is without plasterboard. This is with the this is without plasterboard for the glass fiber insulation, reflective insulation. Here you see the values, and with the plasterboard we get really close one to the other. So they're both really airtight. Yeah? And we also did tracer gas measurements, and you see 0.03 air changes per hour versus 0.04, so really airtight. We wouldn't have a lot of loss through infiltration. Then we equipped the whole thing with a lot of different sensors, temperature sensors, heat flux meters, air velocity sensors. And here you see position of these sensors. These are the temperature sensors. Here we have heat flux sensors in the clear part of the wall, in the cavity of the wall, of that roof, excuse me, and here at the rafter. And in different positions, because we wanted to make sure that we don't measure just one feature. We're really sure that our values are close to each other. Yeah? And therefore, we measured it in 3 axes over the height of the roof. We did a lot of data acquisition, and when I go over that, and these are the results that we've measured. Yeah? These are the in situ R values that we've measured. Here for the glass fiber, and here for the reflective insulation for the different axes here. And you see they don't vary a lot. So this is a quite good measurement, more or less. And if you take the mean, would get here R36, and here R11. So this is the result if you look just to the in situ R values and compared to the predicted ones. I think we got really good, really close to that. Yeah. However, there's one thing that I have to mention, that there's a difference, and you also see it here, between the R value measured here and there. And this would indicate that there is still some kind of airflow. Buoyancy airflow going out here, coming in there, that would explain that difference in the R value. So we think even if you have very good air tightness, there might be some smaller convection effects which are not important for your thermal performance, but which might play a role if you look to the moisture performance, yeah? Because you can get a little bit of condensation. You get more condensation when you have the very slow flows. We'll get to that in the end. And this is now what is important. We measured the in situ R value, but when we looked at all the other field tests, they just looked at the energy consumption. So we wanted to know what was the energy consumption, what's the difference? And here we found, if we take the total attic space, we found a difference of 2. So the energy consumption in that attic with the reflective film insulation was twice as high as in the other one. If you now look at what amount of energy went through the floor, jam balls, gables, and so on, your infiltration, heat losses, and all that, and deducted from that, then you get to this value, 2.5. So the R values, the difference in the R values was a factor of 3, and here we end up with 2.5, which is pretty good because you also have to consider that you have thermal bridges at the rafters and so on, and they also come into play here. Yeah? But I think we could prove here that the mineral fiber insulation does work well when you have an airtight system. And if you don't have it, then you can get results as we've seen before, because the film insulation is intrinsically airtight. Yeah? Okay, let me come to summarize the results and give you some conclusions. I think we've seen here that air tightness is very important, and if you have wind washing effects and it's not airtight enough, that can significantly reduce the thermal performance of mineral fiber insulation. And without the claims of the reflective film insulation manufacturers, we wouldn't have found out, I think. We would just have assumed that what we measure in our hot boxes is what we get in the field. And apparently, that's not always the case. We've also seen that even that the best practice airtight structures still have some airflow that could result in condensation in a moisture source, and therefore in the German standard we now assume that in wintertime due to air convection, you get an additional moisture source of 250 grams per square meter. It does not affect the thermal performance, it just affects the moisture performance. And we've also seen that the reflective films that are currently available are unable to meet the energy requirements. You need additional insulation. And I think this is also very important. And this is a point we're still fighting with the manufacturers of these insulation materials. When we want to summarize the interior insulation challenges that we are faced with in Europe at the moment, we first of all see that retrofitting of existing building is a fast-growing market all over Europe, and not only Europe. And we also see that interior insulation retrofits offers new opportunities for very low thermal conductivity materials, and maybe also for capillary active materials. So for materials that are more expensive than standard insulation materials. We've also seen that the drying rate exposure and the water absorption of the existing walls must be analyzed before you apply interior insulation, in order to avoid frost damage or other problems. And we might have to change some of the criteria in ASHRAE standard 160 if we want to accommodate that concept of capillary active insulation, because you will get higher relative humidity than 80%. And up to now, only 80% on a monthly mean basis is allowed. If we look to the insulation materials and systems, we have seen that the rising energy requirements all over Europe now have led to development of new or improved insulation materials. We've seen that VIP and nano insulation face new opportunities due to the constraints connected with thermal retrofits. It's lack of space, or you don't want to change the appearance, and therefore sometimes you don't have another choice but to take such a high performance insulation material. I think, and this is also important, that the combination of different insulation materials and systems for a single job becomes more common. So the installers must be able to handle the different materials and also application techniques, because in the clear wall you might use rather inexpensive material, but if you go to the window openings, you need something else. You need a higher performance materials. And then you have to join them at some point. And I also think that insulation manufacturers should provide climate-specific insulation guidelines and best practice examples, because it depends a lot on the climate how your interior insulation would perform. Because if you give solar vapor drive a lot, then you might need something else. Different material, maybe some more permeable material, but you also have probably less problems with condensation. And this concludes my presentation. I thank you for your attention.